Okay, so let's look at the Test 2 review. We're also going to be doing the extra credit for Test 2. Going to go through every single one because I want you guys to be very well prepared for that test that's coming up. Okay? So, number 1, rewrite Newton's first law of motion in your own words. I'm not going to write it down, but we will talk about it. So, first law of motion says that if an object has a constant velocity, it will maintain that constant velocity until it is acted upon by an outside unbalanced force, meaning that if anything is going the same direction at the same speed, all forces on it are balanced out. That also includes things that are stationary. If something is stationary and it's staying that way, that means that all the forces on it are unbalanced. Any object that is accelerating in any way will have an unbalanced force. Okay, name of the first law. It's the law of inertia. Number 2, rewrite Newton's second law in your own words. All right, so Newton's second law is just F equals ma. No reason to mince words about that one. It's F equals ma. Name of the second law? Law of mass. Sorry, law of acceleration. Next one, rewrite Newton's third law of motion in your own words. So that's equal and opposite forces. If you have interacting forces, all right, so my left hand is pushing on my right hand. They are both pushing with an equal force, but in opposite directions. Okay? Name of the third law, law of interactions. When you're moving in a circle, what direction is the unbalanced force? There are 2 ways to think about that. The first is in terms of velocity. All right? So acceleration is change of velocity. Part of velocity is the direction it goes in. If I change the direction, I have changed the velocity. It doesn't matter if they're going the same speed. If they're going different ways, the velocity is changed. Therefore, there will be an acceleration. The other way to think about it is putting Newton's first and second law together. Okay? If you've got a change in direction, that means there's an unbalanced force. Okay? Unbalanced force, looking at F equals ma, means that there will be an acceleration. Okay? So, we have a... Oh, wait, hold on. I was just answering number 8. Number 7, when you're moving in a circle, what direction is the unbalanced force? The unbalanced force will always be towards the center of a circular motion. All right, now looking at number 9. A 6-kilogram bowling ball is pushed down a bowling lane with an applied force of 25 newtons. Okay, so we've got mass equals 6 kilograms. We've got an applied force of 25 newtons. Okay, in this one it says that our net force is 23.2. Okay, so F net equals 23.2. All right, and is in the direction of the applied force. What is the friction acting on the ball? So for this, we need to think about what the definition of net force is. F net is the sum of all of our forces. Okay, so the 2 forces we've got on this thing are Fa and friction. Okay, so our net force is equal to the sum of the 2 of them. We know what F net is. It's 23.2. And we know what our applied force is. It's 25. So looking for our friction, we're just going to subtract that over. So 23.2 minus 25 gives us a friction force of negative 1.8. The negative just means that it's in the opposite direction from our applied force. So we've got a friction force of 1.8. Next one, what is the coefficient of friction on the bowling lane? Okay, so the formula we've got that has coefficient of friction in it is this one, where your friction force equals mu, your coefficient of friction, times your normal force. Okay, so we know what our friction force is. It's the negative 1.8. Okay, but we don't know what our normal force is yet. Okay, so let's look back at our problem. It tells us what the mass is. So if we think about our bowling ball sitting on the ground, okay, it's got a downward force equal to its weight, and it isn't accelerating through the ground, which means there must be some upward force from the ground on the ball equal to our normal force. These 2 forces will be the same size. Okay, we have a formula for weight that is mass times gravity. Okay, so if we can find our weight, we'll know what our normal force is. So we're just going to replace this normal force here in our formula with our weight, basically. So our mass is 6 kilograms, and gravity is 9.8. Okay, so solving for mu, that's just going to be our friction divided by our normal force, and that'll give us mu. So negative 1.8 divided by 6 times 9.8. Okay, so we end up with a coefficient of friction of 0.0306. Okay, now do notice there is a negative on there. The negative is on there because we said that our friction was in the negative direction. Whenever you're doing your coefficient of friction, it doesn't actually have a direction. It's just a ratio of two forces, so it doesn't need that negative on there. Your coefficient of friction does not have direction. Okay? All right, next one. When the ball is at rest, it takes a force of 4 newtons to move it. What is the static coefficient of friction? So again, we're solving for mu, okay, which is equal to your friction force divided by your normal force. Okay, in this one, it tells us that the friction that we have to overcome to start moving it is 4 newtons. Okay, so it's telling us that our friction force is 4. Our normal force will still be the same because it's still based on the weight of the object on the ground. Okay, so in this one, we're doing 4 divided by 6 times 9.8. Okay, so for this one, we ended up with a coefficient of friction of 0.0680. Okay, notice that your coefficient of kinetic friction will be smaller than your coefficient of static friction. All right, so that is number 9. Let's look at number 10. Okay, so for 10, it's telling us that Boris has a mass of 120 kilograms. Okay, and we're looking for his weight on Earth. So weight is just mass times gravity. So 120 times 9.8. Okay, so we end up with a weight of 1,176. Okay, so 120 kilograms, that's like 260 pounds. Okay, so newtons, a weight in newtons will be significantly larger numerically than a weight in pounds. All right, so he's not 1,176 pounds, he's like 40 pounds heavier than me. All right, so gravitational acceleration on Jupiter is 24.8 meters per second square. What is Boris's weight there? Well, we're going to be using the exact same formula, but instead of using 9.8 as our acceleration, we're going to be using 24.8 because he's on a different planet. So 120 times 24.8. Okay, so his weight on Jupiter increases to 2,976 newtons. Okay, and then the last question on there, what is Boris's mass on Jupiter? Mass doesn't care what your acceleration is. Your mass is quantifying how much matter is there. Okay, it doesn't matter where you're going, your mass will still be the same. All right, number 11. Store has a mass of 100 kilograms and is running west. Wessel has a mass of 130 kilograms and is running east. They collide head-on. During the collision, Store exerts a force of 1,000 newtons on Wessel. What force and magnitude and direction did Wessel exert on Store? So A is asking about Newton's third law of motion. All right, so Store is exerting a force of 1,000 newtons on Wessel. So according to Newton's third law of motion, Wessel will also be exerting 1,000 newtons onto Store. So it'll be 1,000 newtons, okay, but what direction will it be going in? Okay, so when they're running into each other, we've got Wessel going to the east, and we've got Boris going to the west. Boris will be exerting a western force on Wessel. Wessel will be exerting an eastern force on Boris. The forces that they're exerting will be in the direction that they were moving. Okay, so what force, magnitude, and direction did Wessel exert on Store? So Wessel was moving to the east. So the force that he exerted was to the east. Okay, B, calculate the magnitude of Wessel's acceleration. Okay, so we've got his force, we've got his mass, so we can just use F equals ma, where force is 1,000, their mass, we're looking for Wessel, which is 130 kilograms, and we're looking for A. So solving for A, we're just going to divide 1,000 by 130, and we end up with an acceleration of 7.69 meters per second squared. Okay, next one, what is the direction of Wessel's acceleration? Well, the force on Wessel was from Store. Store was moving to the west, so that means when they collide, Wessel will accelerate to the west. Will accelerate in the direction of the force that was applied to him. All right, D, calculate the magnitude of Store's acceleration. Well, again, we're using F equals ma. All right, so the force exerted was 1,000, but now we're looking at Store, who has a mass of 100. Okay, so now it's just 1,000 divided by 100, and we end up with 10 meters per second squared. So because he has a smaller mass, he will experience a larger acceleration compared to the other guy. All right, and the force on him, well, that'll be going in the direction that Wessel was going, so it's going to be going to the east. All right, number 12. Tetherball is being blown by the wind as shown below. The angle between the ball and the pole is 30 degrees. Now this is one issue. That says 30, this says 40. Okay, I screwed up. So we're just gonna go with the 40. All right, I'll accept either way. Okay, so we're drawing a diagram of the forces on the ball. All right, we've got our ball here. Force pulling it down, we've got our weight. Force pulling it out to the side would be our wind. I don't want to use FW again, so I'll use applied force. Okay, and then the force that's keeping it from falling down and to the right would be the rope, which is applying a tension. All right, so these are the three forces that are acting on it. We can break our tension force up into two components. Make sure that they're dotted lines to show that they are merely components of a force, not an actual force acting on the ball. Okay, when we're looking for the weight of the ball, well, we've got a formula for that. FW is equal to mass times gravity. So the mass of the ball is 5 kilograms, gravity is 9.8. So plugging and chugging, that's going to give us 49 newtons. All right, so this downward force here is 49. Now, if we're looking for the force due to the wind, there's something very important that we need to look at in this problem that will help us. It tells us the net force on the ball is 0 newtons. That is a very important aspect of this problem. That means that all of the forces acting on the ball are canceled out. Any downward forces due to the weight will cancel out with any upward forces from the tension. The side-to-the-side forces, so the force to the right from the applied force of the wind, will cancel out with the force to the left from our tension. Okay, so what we've essentially got is a triangle up here that has an adjacent side equal to 49 because our weight is 49. It has to cancel out. All right, so when we're looking for the force due to the wind, all right, the wind is pulling to the right. It has to be equal to the force pulling to the left because the ball has a net force of 0. So when we're looking for that applied force from the wind, what we really need to find is the opposite side of this triangle. Okay, so looking at that triangle, let's redraw that. We've got an angle of 40. We've got an adjacent side of 49, and we're looking for this opposite side over here. So a trig function that has opposite and adjacent would be tangent. Tangent of our angle equals opposite over adjacent. We're looking for that opposite side. So we're just going to multiply our adjacent side over. All right, so that opposite side, the force due to the wind, will be equal to our 49 times the tangent of our angle. Now your answer might be slightly different if you were looking at the typed letters instead of the written ones. You might be doing 49 tangent of 30, all right, which will give you a slightly different number, but the process of getting there is still the same. So we end up with 41 newtons side to side. Okay, so now we've got another side of our triangle, 41. All right, now if we're looking for the tension on the rope, well, that rope was pointing off along this hypotenuse here. All right, so we're just looking for the hypotenuse of our triangle. Easiest way to do that is just to use the Pythagorean Theorem. So 41 squared plus 49 squared equals our tension squared. All right, so we're going to do 41 squared plus 49 squared, and then take the square root of it. Oh, I put it in a negative. Why did that even happen? There we go. So that gives us a tension force of 63.9 newtons. There we go, we've got our tension. All right, I'm gonna pause it real quick because my phone is running out of memory. I need to delete some old note videos. All right, so jumping back in. It's no longer giving me a warning that my memory's full. Good. All right, so number 13, we've got a ball tossed horizontally off a 20-meter cliff with a velocity of 12 meters per second. So what we know is that our horizontal speed is 12 meters per second. We've got a vertical distance of 20 meters, and we're dealing with a projectile, so we know the gravitational acceleration is equal to 9.8 meters per second squared. Okay, so now if we're looking for the ball's initial vertical velocity, it told us that the ball was tossed horizontally. That means that our initial vertical velocity is 0. If you've got an object being tossed horizontally, it does not start off with any vertical velocity. What is the ball's final vertical velocity? Well, now we're going to be using kinematics, so all of this stuff is vertical. This is horizontal. We're not going to include that. It doesn't matter. All right. So looking at our vertical stuff, we've got initial velocity, acceleration, distance, and we're looking for final velocity. So that means we're looking at formula C, where our final speed squared equals our initial speed squared plus 2 times our acceleration times our distance. Okay, I just replaced it all with the vertical versions. Now, our initial speed is 0, so that part goes away. So essentially what we've got is our final speed equals the square root of 2 times gravity times our vertical height. Okay, so square root of 2 times 9.8 times our vertical height of 20 meters. Okay, and then we're just gonna plug and chug. So square root of 2 times 9.8 times 20. That gives us a final vertical velocity of 19.79, which will round up to 19.8 meters per second. Okay, and because this thing is going downward, right, it's falling down a cliff, and we already said that gravity was in the positive direction and our displacement was in the positive direction, we're just going to leave that as a positive number. All right, so there's A, and my light's turned off, and I'm just going to keep on going because it's generally bright enough in here to still read. All right, how long does it take for the ball to hit the ground? Okay, so now we're looking for time. At this point, we've got our final velocity, we've got our initial velocity, we've got gravity, we've got distance. Let's use formula A. Why not? So A equals VF minus VI over T. Okay, so solving that for time, it's going to be equal to our final velocity minus our initial velocity, all divided by our acceleration. Okay, plugging all that in, we've got 19.8 divided by 9.8. That gives us a time of 2.02 seconds to hit the ground. Okay, what is the range of the ball? Now, this horizontal stuff is important, okay? Because when we're looking at horizontal, there's no acceleration. Okay, your horizontal speed does not change, which means that we can use formula 0, where a horizontal speed is equal to our distance divided by our time. Looking for our distance, we're just going to multiply our time on over. So that'll be our horizontal speed times our time. So 12 times our time of 2.02. Okay, so this times 12, and we end up with 24.2 meters. There we go. All right, so there is number 13. Let's look at the next one. The same ball is thrown at 30 degrees above horizontal with a velocity of 15 meters per second off the same cliff as number 13. So 30 degrees above horizontal means that our ball is being thrown with a hypotenuse of its speed vector of 15 and the angle being 30. Okay, we're looking for the ball's initial vertical velocity. So vertical velocity is this side of this triangle. Okay, so our opposite side. All right, so the trig function that has our hypotenuse and our opposite side would be sine. Okay, so sine of our angle equals opposite over hypotenuse. All right, we're looking for our opposites. We're going to multiply h on over. So opposite is going to be equal to our hypotenuse times sine theta. All right, our hypotenuse is 15 times the sine of our angle, sine of 30. Okay, so 15 times the sine of 30. That gives us 7.5 meters per second vertically. Okay, so there's our initial vertical velocity. Our initial horizontal velocity will be the adjacent side, the side that is going horizontally. So let's use cosine. Okay, so cosine of your angle is equal to the adjacent side over your hypotenuse. We're looking for that adjacent side, so we're going to multiply h on over. All right, so a equals h times cosine theta. All right, so our hypotenuse, we got 15 times the cosine of 30. Okay, so 15 cosine 30, which gives us 12.99, which is just 13 meters per second. Okay, so now we've got both of our sides. This was our vertical, and this was our horizontal. All right, how long does it take for the ball to hit the ground? Okay, so looking at our ball, we've got our initial vertical velocity, we've got the distance that it's falling, 20 meters, and we've got gravity. Now, if we want to solve for time with that, it actually is kind of awkward to find because we'd have to use formula B solving for t, which I don't recommend anyone do. Okay, so instead of solving for time first, let's solve for our final velocity first. Okay, so VF squared equals VI squared plus 2ax, right? Because we've got all of these values. We know the distance it's falling, we know acceleration, and we know its initial speed. Okay, so moving our stuff around, getting that squared off of there. Okay, so this will be 7.5 squared plus 2 times our acceleration of 9.8 times our distance, because it is the same cliff as what we were looking at number 13, of 20. Okay, so 7.5. Hold on, before I plug that in, let's look at something very important. The direction. Okay, it says that it was thrown above horizontal, so this 7.5 is upward. All right, this gravity and this displacement are both downward because it is falling down that cliff. It is being accelerated downward due to gravity. Okay, so we need to make sure that either up or down, one of them gets negatives on it. Let's make down negative for this one. Okay, so I'm putting a negative on each of those. My number here, according to my calculator, wouldn't have changed, but we do need to think about which direction is which when we're figuring out what sign to put on our answer. Okay, because your square root is technically plus or minus, right? It's telling us 21.2 meters per second, but which direction is it? All right, it's going downward, which we said was negative in this problem. So we're going to make that a negative 21.2 meters per second. Okay, but our whole goal was to figure out how long it was taking, so now we're going to use that to figure out what our total time is. Okay, so let's look at formula, why not D? Yeah, so x equals 1/2 VF plus VI times T. Okay, we're looking for time, so let's move our stuff over. So that would be 2x over VF plus VI equals T. Okay, our distance was the height of the cliff, so 20. So 2 times 20. Our final speed was what we just found, so the negative 21.2. Our initial speed was 7.5. And we're looking for our time. So if we hadn't put that negative on there, if we hadn't thought about what direction things were going in, this would give us a vastly different time. All right, so now we've got 40 divided by our negative 21.2 plus the 7.5 that we found earlier. And that gives us, forgot one more thing. This thing is being displaced downward. So that is technically a negative 40 there, which is going to get rid of the negative on here. I was just talking about being consistent with your directions, and I screw it up. Dang, dang, dang. All right, so we end up with a time of 2.93 seconds. Okay, so make sure that you're being consistent with your ups and downs as to whether they are positive or negative, especially if something is changing direction while it is being accelerated. Okay, so what is the range of the ball? All right, well, that's just looking at your horizontal stuff. So Vx equals x over t. All right, we're looking for a horizontal distance. Okay, so that will be your horizontal speed times your time. In this case, it will be 13 times our time of 2.93. Okay, so 2.93 times 13, and we end up with a horizontal distance of 38.1 meters. There we go. All right, our next one. All right, so two objects of different masses are dropped at the same time from rest. Which will hit the ground first and why? All right, so what is gravity pulling them down? It's just 9.8 meters per second squared. No part of that mentions, hey, what's the mass of the thing being pulled down? Gravity doesn't care what you are. It will pull the same regardless. The only thing that will make a significant difference in how long it takes for something to hit the ground is how much air resistance it has, okay? And as I've said before, we do not care about air resistance in here because we're looking at objects with a negligible amount of it, simply because air resistance is hard to calculate. All right, so if we drop two objects with different mass, here they are. Hey, look, they both hit the ground at the same time. All right, so unless you're doing like a bowling ball and a feather, they're gonna hit the ground at the same time. All right, an object is thrown horizontally while the other is dropped from rest. Which will hit the ground first? We demonstrated that when we were looking at our resultant notes. Right? Think about the bouncy balls where I threw one horizontally and the other one I just dropped. All right? As soon as they are released vertically, they are accelerating downward. All right? The horizontal velocity means nothing. It's all about the vertical stuff as to whether it hits the ground at a certain time. Okay? So they will hit the ground at the same time because gravity is accelerating both the same, and they both started with the same vertical velocity. All right. A force of 20 newtons east and a force of 5 newtons south are exerted on an object. What is the magnitude of the net force? Okay. So we've got a force to the east of 20. We've got a force to the south of 5. All right, and we're looking for the magnitude of the net force. So that is just looking for the length of our hypotenuse. All right, so that would be 20 squared plus 5 squared equals our net force squared. Okay, so 20 squared plus 5 squared, taking the square root of our answer, and we end up with 20.6 newtons. All right, so when it asks for magnitude, it's just asking, hey, numerically, what is this thing? Direction of the net force. All right, so looking at this, this is our smaller angle. It'll always be adjacent to the longer side, so we're finding the angle there. We've got those two sides. Let's use tangent. All right, so tangent of our angle equals our opposite side, which would be the 5 newtons, divided by our adjacent side, which would be the 20. Okay, so looking for theta, we're taking the inverse tangent of 5 over 20. Okay, so inverse tangent of 5 over 20, we end up with 14.0 degrees. Which direction is that going? Okay, so our cardinal direction for our adjacent side is to the east, and it's being pulled to the south of there. So this would be 14 degrees south of east. Cool. Next, the object has a mass of 10 kilograms. What is its acceleration? So we got F equals ma. All right, we know the force is equal to 20.6, and we know that our mass of the object is 10 kilograms. And we're looking for our acceleration. Okay, so dividing that 10 over, we're going to end up with 2.06 meters per second squared. It will be in the same direction as our net force. So 14 degrees south of east. Cool. That was a terrible circle. It covered my decimal. Whatever. All right, next one. Force of 20 newtons is applied 25 degrees north of east. Okay, so we've got 25 degrees north of east. Okay, so our adjacent side is our eastern one, and we're being pulled to the north of there, and we've got a force of 20 newtons. That's telling us our hypotenuse. All right, so what is the magnitude of the eastern component? That's looking for our adjacent side. So we've got our hypotenuse, we're looking for our adjacent, so we're going to be using cosine. All right, so cosine of theta equals our adjacent over our hypotenuse. Looking for our adjacent, we're going to multiply h over. So h times the cosine of theta. All right, our hypotenuse is 20, cosine of 25. All right, so 20 cosine 25, 25, there we go. And we end up with an adjacent side of 18.1 newtons. So that is that side right there. Okay. Next, we're looking for the magnitude of the northern component. Well, we've already got two sides of it, so let's just use Pythagorean Theorem. So a squared plus b squared equals c squared. All right, we're looking for b. That'll be the square root of c squared minus a squared. Okay, so we're going to do our hypotenuse squared minus our adjacent side squared, and then take the square root of that, and it leaves us with a northern component of 8.51 newtons. Okay, so we've got our two sides. Last one, which I guess is in two pieces. We're looking for a velocity and acceleration graph for each of these. So a velocity graph is the slope of your displacement graph. All right, so looking at our displacement graph, it starts off flat. Okay, so the slope of a flat line is 0, and it's flat for the entire time up until we get to that point. After that, our slope goes negative. Okay, so our velocity should be going from 0 to negative. All right, your acceleration graph is the slope of your velocity graph. Okay, so the slope for that first section is flat, it's 0, so our acceleration will be at 0. The slope of the second section is negative, and it's constant for the entire time that it's sloping down. So we should have a constant negative acceleration. Okay, so there's our graph for the first one. Let's look at the second one. Okay, so for this one, our velocity graph, still split into two pieces. Our first section is going up at a constant rate. We've got a constant positive slope, so that means our velocity should be constant and positive. All right, here we've got it flatlining. Okay, so our velocity should be 0 because we have no slope in that whole second segment. Okay, looking at our acceleration graph, the slope of this flat section is 0, so we should have an acceleration of 0. Slope of this second flat section is also 0, so an acceleration of 0. Okay, so there are all of our graphs. That was the first review. I'll put up a separate video of the second review just because this one's going to be a little bit long.